Hey guys, how's it going? In this video, I'm going to solve this Leetcode problem again. Actually, I solved this problem, but it was used another approach, was an iterative approach. In this video, I'm going to solve it by using a recursor, um, which is slightly more intuitive, I think. But this approach is not as fast as the approach that I used before, so feel free to browse the other video as well. So the problem that we're looking at today is the kth. Smallest element in a binary search tree. So this question was asked by in the past 6 months by Amazon, Facebook, Microsoft, Adobe, and eBay. And so let's dive into this problem. We are given a root of a binary search tree and an integer k. So we need to return the kth smallest element in the tree. And let's look at the binary search tree. Looks like this, and the number on the tree is sorted in a particular order. So everything on the left will be smaller than the root node, and everything on the right will be bigger than the root node. So 1 is smaller than 3, 4 is bigger than 3, and 2 is bigger than 1, right? And in this example, we need to find the smallest number, which is 1. So we have to return this number. And for this tree, k is 3, so it's the third smallest number. So we can see the smallest number is over here. The second smallest number is 2, and the third smallest number is 3. So we have to return this number. As you can see immediately, the number on the left is all the smallest number. And now they added a follow-up question, and this is another reason why I want to come back to this question. And the follow-up question was, if the binary search tree is modified often, in other words, we do insert and delete operations, and you need to find the k smallest number frequently, and how would you optimize that? I'm going to discuss this follow-up question at the end. I'm going to show you this simple recursion method first. So this is the implementation. As you can see, so the code is pretty clean, right? So we need to have a recursor function. So if there is something on the left and there's something on the right, and we append the list, and at the end we will return a sorted list, because again, by that rule that we talked about before, everything on the left will be smaller and everything on the right will be bigger, and everything on the root node itself will be somewhere in the middle. And this is how we can concatenate a list. Looks like this. And then if there's something on the left, we push the left node back to the recursor, and then do the same operation again. And if there's something on the right, we do the same thing. If there's nothing on the left, but there's something on the right, and then we call the recursor on the right. Same for the left. If there is something on the left, but there's nothing on the right, we just call it recursively call the function on the left node. And there's nothing on the left and nothing on the right. That means this node is a leaf node. Just return the list that contains the number itself. So let me show you the sorted list that which is returned. It's exactly sorted this way: 1, 2, 3, 4. And then after that, it's easy, right? We just look up the list at the kth element. And also it's k minus 1 because we are talking about index, and this one works. Okay, so now let's talk about the follow-up question. Actually, this is a object-oriented design problem. For a binary search tree, the inserting and deleting takes a big of log n time for a balanced tree. And the official solution uses a doubly linked list, which was used in the LRU cache design problem. If you haven't seen this problem before, and feel free to check out my video. I have one of the videos that talk about the LRU cache problem. So this official solution talk a little bit about how to implement it. So let's say it gives an example. So let's say if we want to insert 4, and we have a tree looks like this, is completely balanced, and 4 is smaller than 5, so it's go left, and 4 is bigger than 3, so we go right. So we go left first and go right, and then we find the correct position for the number 4 on the tree, and then we actually have to convert. Actually, it's not converting. We have a corresponding doubling linked list that is corresponding to the tree. Okay, so everything on the left is smallest, everything on the right will be biggest, and then the number 4 is somewhere in between. And the reason why we need a duplicate linked list is because we need the ordering. And I think the solution is overly complicating the solution, because I think we can just use a regular array list. The index, right? The smallest index will be the smaller number. The bigger index will be a bigger number. I think it's a lot easier to implement than a duplicate linked list, which we can do that actually, as you can see. But I don't think it's necessary. So again, it talked about the time complexity for inserting is big over h. H is the big log n, and the searching takes a big of k. And also it talks about space complexity, which is it's the newly created duplicate linked list. So this is my second solution to this problem. I hope this is helpful. If it is, please like and subscribe. That would be a huge support. Thank you so much for watching. I will see you in the next video.